our load calculations are never going to be 100% perfect because we can't always get every single nuance of a house into that mathematical calculation. There's a little bit of squish in there. And I've seen that a lot of manual J calculations tend to overstate heating a little bit. So a lot of times what we hear is, oh, well, the heat pump won't heat the house anymore. So now I have to shut that off, go into emergency heat, and now I just want to run straight electric heat. Well, why? I'm still getting way more value for my money down here with that heat pump.
Hi, and welcome to the Heat Pump Podcast. I'm Ed Smith.
And I'm Eric Fitz. We are co-founders of Amply Energy.
So we are very grateful today to have the one and only Eric Kaiser, who around the halls of TruTech goes by Elk. And given that we have Eric Fitz here, we're going to call him Elk here too, just to make everything easier. Elk, thanks for joining.
Hey, thanks for having me, guys. And that's why I got the name Elk. A, it's my initials, and B, because when I joined TruTech, there was a second Eric here. So yeah, makes it a lot easier.
All right, well, delighted to have you. And we're going to get deep into heat pumps. You gave an incredible presentation at Heat Pump Summit last June, and then you gave another great presentation on heat pump performance at NCI in Carolina in September. Both were great, so we wanted to bring you on to talk about some of that stuff. Before we get too deep there, you got your own podcast with Bill Spohn. You're on a bunch of these all the time. You're always asking folks to tell a little bit about themselves. I feel like I don't have the Elk backstory. Would love to know career trajectory and how you got to where you are today.
I'm going to say a lot of dumb luck and stumbling onto things that I like as I progress through life. And started years ago, when I was a little kid, I was homeschooled, never been to public school, just learned as I went along a lot with that. And my dad was in charge of maintenance for a little college in the town where I grew up at in Illinois. So he did all of the electrical and plumbing maintenance for that college. And along with that went telephone systems and energy management systems and all kinds of other things. Because when you're in a small organization, as a lot of your listeners probably know, you wear a lot of hats. So that's what I grew up around. He was also very big into many different energy sources. I think currently he has 4 different sources of heating in his house. There's passive solar. There is a heat pump. There is a hot water coil and some ductwork that's hooked to an old water heater. And a wood stove.
Nice.
Amazing.
So I grew up around some very creative things. And actually, you mentioned the Building HVAC Science podcast, which I'm on co-host with Bill Spohn. We actually had him on there to talk to about a few of those things and some of the stuff that he's done and some of the iterations that he made, because over the 40 some odd years he's been in that house now, there have been a lot of iterations to it and a lot of things changed. He's installed solar electric on there and played with that for years and done all kinds of stuff. So that's what I grew up around. And then I transitioned into doing a lot of different stuff and ultimately landed in 2004. I landed into HVAC, actually through my former father-in-law. He asked me to join his company and I fell in love with the trade. I started learning and I've just continued to go from there. Started out in the residential as a service technician, ended up moving from Illinois to Indiana, and went into doing residential retrofit installation as well as some service. Transition from there into more commercial and industrial work, where the company I worked for did everything from small rooftop units to boilers and chillers and large rooftop units, schools, manufacturing facilities, things like that. And then went into, got an offer to go work for a distributor locally and do technical support and training for them. And I had really kind of fallen in love through being in some RSES chapters, which is the Refrigeration Service Engineers Society, which is now combined with RETA, which is the Refrigerating Engineers and Technicians Association. through some of those organizations, I had really fallen in love with teaching and training. And I felt at that point that I had had some really good mentors in the trade and wanted to pass along the knowledge that I had, along with gaining new knowledge, being able to pass that along as well. And I had a lot of fun with that. I really enjoyed it. And as I kind of progressed through that, decided to go out on my own, worked with that for a little while, had some contracts with some various organizations, developed some training, presented training, and ultimately Eric Preston over at TruTech Tools, which Eric is no longer with the company, but at the time they were co-owners of the company. They came to me and said, hey, we want you to come work for us. And that's how I landed at TruTech Tools. My job title is Industry Engagement Manager because my job is to go out and engage with the industries, bring information to the industries, as well as take information back into TruTech and make sure that we're doing the right thing for the industries that we serve, which is the HVACR and building performance markets. An internet distributor of products for that realm. And with that, I'm also kind of the technical guru within the company. Between Bill and I, we know a lot about how to do the testing in the field. I bring a lot of the field experience that I had in the HVAC markets. While I was working for myself, I also did some building performance testing, got into doing shell testing and duct testing, and really diving deeper into those hard-to-fix comfort complaints that homeowners often have. So that's how I've gotten to where I am at now.
Elk, would you put dates on those for me? Because 2004, you got into HVAC.
Yep.
And then when did you go to work as a trainer at the distributor? When did you go out on your own? And when did you start at TruTech?
Okay, 2015, I went to work for the distributor. And then went on my own in 2018. I think I started that in 2018. And then TruTech, I did about a year they had hired me as a consultant for about a year, and I did some work for them prior to coming on full-time. And then I started full-time with TruTech in 2023.
Actually, I remember your podcast with Bill introducing you as new to TruTech. I think you'd been there for a couple months, but that was one of the first Building HVAC Science podcasts that I listened to.
Nice.
That was great to get your background. Let's talk about heat pumps. Fitz, do you want to start us off, or you want me to?
Sure, I'm happy to jump in. So we're really excited about a couple different things. We know that you were part of the Manual S review committee. For those of folks that aren't aware, there's a new version of Manual S out there. It's actually a great decision by ACA to make the normative section available publicly for free, which is fantastic. So you can go check that out at ACA's website. So we're excited to talk about Manual S a bit and get into the areas that are specifically relevant for heat pumps. Man, there's all kinds of fun heat pump design specific things that we would just, based on your own podcast and other conversations we've had, that we'd love to dig into. So why don't we start with just talking a bit about kind of homeowner expectations and why that's important for the design process, and why is that an important place to start in the design process?
Oh, I love that, because homeowners can be challenging. Well, people can be challenging in general, but a lot of times homeowners will say one thing and kind of mean something else, but not realize they mean something else. What I find when I dig in with homeowners is ultimately what they really want is comfort. They want to be comfortable in their own space, and they want to do that as inexpensively as possible. They want the most inexpensive installation they can get, and they also want the most inexpensive utility bills that they can get. But ultimately, they want to be comfortable. And what I think we forget a lot of times is that sometimes comfort comes at a price. Well, anytime comfort comes at a price, because we have to build a good shell to be comfortable. You know, if we're sleeping or living in something like a corn crib, and the wind blows through it, and you can feel that wind blowing through it, it's probably not going to be really comfortable indoors unless it's comfortable outdoors. So we really have to understand what that is the customer wants, and we can do that by asking some questions. But if we don't have a good understanding of what that customer actually wants, not necessarily what they say, because they might say, hey, I need a new furnace, or I need a new air conditioner, or I need a new heat pump. We need to dig past that and say, okay, what do you expect for comfort? And ultimately, that's what we need to find out. Now, there are different ways to ask that, because a lot of times if a homeowner says, what do you expect for comfort? If you ask that question straight up, what do you expect for comfort? They're going to give the answer they think you want to hear, which is probably going to be, hey, I want to maintain XYZ set point in my house all the time. And as we've found out, if you've ever listened to Robert Bean or somebody like that, you're going to find out that maintaining an air set point, an air temperature set point, does not equate to human comfort. That has to be top of mind. It should be top of mind no matter what kind of HVAC system we put in, but it's especially important. What I've found is in heat pumps, it is especially important.
You mentioned that there's a number of ways you can kind of try to get at those or ask those questions to get at really the information you need that's going to help you with the design process that you could recommend.
Well, one of the questions that I like to ask, and it's kind of backward, it's kind of going into it back end, is what are your favorite parts of your house to be in? And why are those your favorite parts of the house to be in? That gets people started down that road of thinking, okay, why do I like to be here? And from there, you can say, okay, if you like to be here, why don't you like to be somewhere else in the house? That'll open people up a little bit more in my way of thinking. And from my experience, it starts people really thinking about what they enjoy. And I want to find out what people like, because that's what I'm driving for. I want to go for what somebody enjoys, and I want to deliver that to them.
Awesome. That's such a great way to go about it. I think about, various houses I've lived in where you're like, man, it's really comfortable to be here in the morning, but man, I have to have all the blinds down and it's super uncomfortable in, the afternoon every day. And like those kind of messages really help you understand, whoa, okay, so we've got some issue with afternoon sun in this location. We got some solar gain problems. Not only is it uncomfortable from a light perspective, it's getting hot. Yeah, I love that technique.
Yeah. I also like it. In many states, rebates are a big topic with heat pumps. And so when a comfort advisor walks in the door, sometimes what they hear from the homeowner is, I want to maximize my rebates and get a brand new HVAC system. And then sort of the comfort advisor is off from there. Whereas if you ask this question, like where your favorite place to be, you get away from that conversation and you kind of get to understand the homeowner and what they need from that HVAC system, which I imagine just leads to a cleaner understanding of who you're dealing with and how you can best help them.
Selling to a rebate is really hard, because what if, the rebates often come with specific strings attached, maybe a certain equipment efficiency or other specific items. And if those items aren't right for that homeowner, a lot of times we can do a disservice by selling to that rebate. At least that's what I've seen. And that really is going to depend on what the rebates are and everything else. But rebates, honestly, people get in a mindset of, hey, I'm getting free money or I'm getting some money back to me. And that's great. But if it's not right for you, then don't do it. To me, it's kind of like going to a grocery store and buying something just because it's on sale, but you really don't need that product at home. Okay. I've already got 50 cans of soup sitting on the shelf, and they're the oldest one is 5 years old, but I'm going to go buy 5 more cans of soup because I've got a coupon for 20% off today. Well, you really didn't need 5 more cans of soup at that point, because you haven't eaten up all the soup you bought 5 years ago.
Totally.
So
it's like you came to Costco with my wife and I the last time we went. Extremely well said.
But Elk, I mean, it's such an important point, because in a number of states, rebates are driven based on tonnage. And so it's like a X number of thousands of dollars per ton per system. And man, does that create some challenging incentives that lead to bad outcomes, where, you've done a careful load calc, you've really looked at equipment selection, and you're like, well, if I just go up a full size on this unit, we're actually going to get a little bit more money, and it's going to be lower price. But oh my gosh, you're going to end up with an oversized system and have less comfort.
Yeah, that can very easily happen. And that becomes a real big challenge because a lot of homeowners have the perspective or the belief that bigger is always better. Bigger is going to deliver more comfort. Bigger is going to get it done faster. Well, it might get it done faster in some situations, but when you look at a house, right, the house is always either losing or gaining heat. Now, it's wintertime right here. I got cold on the mind because when I woke up this morning at my house, it was -4 degrees outside Fahrenheit for the people who might listen to this outside the U.S., just to make sure, because -4C is a little bit warmer than -4 Fahrenheit. I'd be comfortable in -4C.
Yeah, quite a bit different there.
Yeah, just a little bit. That house is constantly losing heat. Right. And because our thermostats run on air temperature and not a real good comfort metric, because again, if we go back and we look at true human comfort, roughly 60% of human comfort is radiant heat, not air temperature. Yet we don't sense radiant heat on our thermostats. We sense air temperature. If the equipment is so big that it satisfies that demand and it shuts off, the house is still losing temperature. All the surfaces around us are cooling down. And depending on the insulation in the house, it might be slowly or it might be rapidly. But regardless, those surfaces are going to start cooling down. And by the time that equipment gets turned on, those surfaces are going to be cold again. And then if it's oversized, it's going to come on, it's going to blow out a bunch of hot air. And suddenly we're going to blow in a bunch of hot air, but we're not going to run long enough, more than likely, we're not going to run long enough to warm those surfaces back up to where that's comfortable. Because you really want your surfaces to be kind of close to where your thermostat set point is. Those surfaces should be running, if your thermostat's set at 70, your surfaces in that house should be maintaining roughly 70 degrees on an average, that's where we get into what's called mean radiant temperature of the surfaces around us.
Another guest we had on talked about how in some cases in the state of Massachusetts, the rebates can actually lead you to violate Manual S, and that ends up in this tricky situation. So let's get into design and Manual S for heat pumps to take it to the next level. You've got some slides that you've used in some presentations we've seen. So you'll pull up some of those occasionally here. So for our listeners who are just checking out the pod, this will all be on YouTube. It'll be in the show notes if there's a visual, but it might help a little bit if you check out some of these in the show notes or on YouTube. But let's start with ACCA's system design process, ELK. Can you walk us through that and how the pieces tie together?
Yeah, so we'll bring this slide up here and show this. And this is really the system design. It's a step-by-step design. And each ACCA design manual feeds into the next one. It takes information out of that first part and it keeps feeding down and feeding down and feeding down. And what I've seen is a lot of people really talk about that Manual J, which is a great part, and it's a really complicated part sometimes to get a good job done. But there's a lot of other things that go into, there's things that go into Manual J, and Manual J feeds into a lot more other things that we really need to pay attention to get good comfort in a house. Right? And it starts with the concept of the system, what you're going to do, what's the conceptual idea of that system. Sometimes we can't really change things that are in existing houses. So for me, the system concept is called Manual RS. That's really great for new construction. I don't see a lot of use for it retrofit construction, but it can be useful, I guess, if you want to. But that feeds into the load calculation. And the load calculation simply tells us what the house needs. Right? That's the loss and the gain on the house from BTUs per hour at typically at what we call a 99% number, which is the number that we don't exceed outdoors 99% of the time. And that information is then fed into more things. If you got zoning, you want to use Manual ZR. It also feeds into Manual T, which is air distribution. And a lot of people think of the ducts as the air distribution, but the ducts are more of a conveyance. right? They convey the air from the equipment to the space. And then manual T, what that does is it helps us select the proper registers and register locations for the air distribution in the largest duct, which is the house. If we think of the house or the house or the space as the largest duct in the system, and we want to distribute the air properly in that, it's the largest and low velocity. We don't want high velocity in there. Sometimes we need to put high velocity into certain places, which is where manual T comes in, because we want to put the air in certain spots. And one of the biggest rules, and especially with heat pumps, because we put out lower temperature air, is do not blow air on the occupants. Don't blow air on the people. If you've got a situation where you're going to blow air on people, heat pump, you're going to have to be really, really careful and really intentional in your design, or maybe not go that route, because you want to make sure you're going to have a happy outcome out of this. And if you throw that heat pump in there, those people are probably going to be really unhappy at that point. So manual T then feeds into the duct size calculation. The load calculation feeds into the duct size calculation. And manual S, the load calculation feeds into manual S, which is equipment selection, and that also feeds into your duct size calculation. So you need all three of those pieces, the load calculation from manual J, your good air distribution from manual T, and good equipment selection from manual S to properly do a duct size calculation, which is manual D. And without all that information, you put up manual D, again, is a calculation. Every one of these manuals is really about calculating something. And the better information you put into a calculation, the better the results are going to be coming out. If you don't have all that good information going into manual D may not work well for you. You may have a failure or a design flaw. And then that comes out of manual D, and we take that equipment selection information and the duct size calculation, and we put that into the adjust, test, and balance, or manual B. And that is all about about putting the air where we need it to go. Because just because we put in a duct from point A to point B, and a lot of times we're going to have a piece of equipment centrally, and then we're going to run a bunch of ducts off of that. And we can size our ducts pretty well, but we can't size every one of them perfectly because they come in nominal sizes. And that's where we need to put dampers in. So we've got nominal size, we've got different length ducts. That's why we put dampers in, to make sure that we're going to adjust and put that airflow really where we want it to be. And that's all part of the adjust, test, and balance, putting the airflow where we want it, making sure that everything is set up so that we do have that premium comfort for the occupants.
Beautifully explained. And there is a visual we have up on the screen that can be helpful, but I mean, Elk, that was super clear.
All right.
Just to reemphasize your point about don't blow air on people. It's good practice in general. It's not just for heat pumps, like don't blow air on people. But your point about heat pumps in particular, and air being lower temperature, sure. The air coming off of a heat pump, it's going to be likely over 100 degrees, but moving air, as we all know, just feels cooler to the occupant. And so whether it's in the heating season or the cooling season, if you've got air blowing on you, it's uncomfortable.
Even off of a heat pump, you can get air a lot colder than 100 degrees coming off of it and still heat the space. For instance, my own heat pump in my house, I was looking at it the other day, and what would be the discharge line or the vapor line, the large line coming into that house from the outdoor heat pump, was somewhere, the line temperature was somewhere around 97 or 98 degrees. And this was in, I think it was low teens outdoors. So if I've got a 97 or 98 degree line temperature, I'm not going to get 100 degree air out of that. It's not possible. Don't recall what air temperature I ended up getting out of that, but it wasn't super high. It felt really cool if you throw your hand over that register. But it's still holding the house at set point. And it's keeping my walls, because of in the better part of my house right now, I have redone the ducts to be able to distribute the air onto the surfaces, those outside surfaces of that house. And what I've discovered with that is if I can control those outdoor surfaces really, really well, man, that comfort in there is premium. If I can keep those outdoor surfaces somewhere around that 70 to 72 degree mark and not blow air on the occupants, oh boy, is it comfortable in there. It's been cool. I've had the heat pump sitting around my house for a few years now, and I've been planning this, and I finally got to put it in last year and got it started up in early December, and, of course, rolled right into heating season then. And it's been a lot of fun to play around with it and really be able to dial this in and test a couple of the practices a little bit more in depth because I'm living in it every day.
Can I ask what make and model you installed in your own house?
So I put in a Bosch BOVB 1836,
Okay.
which is their 18 SEER 3-ton nominal heat pump.
And dual fuel, so still with a backup?
No, electric backup.
Electric strip.
Yep,
Nice.
just electric strip heat.
And is that a communicating thermostat, non-communicating?
Non-communicating, all 24-volt control. I've talked about it for a while. I've played around with it, but I've never lived in person with this to be able to really dial some things in. And I've even learned some new things as I've gone through setting this up, which is pretty cool. And I'm going to be getting to share some of those. We'll probably share a few of those on here today, as well as I've got a presentation with Bryn Cooksey coming up at the National Home Performance Conference. And that is called Winter Peaks and Control Freaks, I think.
Oh,
And
nice.
We're going to talk about controlling heat pumps really well in the wintertime. So that's going to be a lot of fun.
Awesome.
And I'm going to get to share some of what I've learned there as well.
That's awesome.
So that overview of the ACA design process was super helpful. Let's dive into Manual S. You were part of the team of incredible people that helped rewrite the latest version of Manual S. Can you just touch on what are the big changes in this version of Manual S versus the prior version?
The team that sat down really wanted to hone in on a few things. And one of the big ones was heat pumps, because there's a lot of focus on heat pumps right now, and especially heat pumps going into cold climates. And where we have a heating dominant climate, heat pumps a lot of times are, they still have to do cooling in the summertime, and we still have to do humidity management in the summertime. But a lot of people are wanting to put heat pumps in to manage 100% of their heating load, so they don't have to run gas heat or electric strip heat or things like that. The group that did a lot of this really wanted to hone in on helping people do a better job of sizing those, being able to carry that heat load, but still manage humidity in the summertime. Because there's a big problem if you're putting in something that's sized for the heating load in wintertime, and it's a heating dominant climate, like my climate here, I'm typically around double my cooling load is my heating load. That's a kind of a general rule. If I've got double that, now my heat or my air conditioner, my cooling is going to be way oversized. So we have to figure out and make sure we're managing that humidity well. So a big part of this was guidance on dehumidification when you have a heating dominant climate, and even on, more humid climates and things like that. So the heat pump sizing tolerances changed there. Better definition and expanded definitions of a lot of the terms in there. So that was really something that group worked on pretty hard. There was a lot of things done to that, and it's quite an honor to be able to sit down and go through that and help with that group, because it's neat for me to get to see that process from the backside. We listened to a lot of public comments, and there was a lot of things back and forth between the group. And if you've ever tried to do anything in a large group like that, trying to find a consensus is challenging sometimes. That was really neat for me, because that was kind of the first, I guess, big project that I worked through from beginning to end. We're updating something like that. And it was very neat to be able to see that process and work through that process from the backside. Never having done the full thing. I'd kind of thrown some comments towards that, but not been involved with the full thing before.
Very cool. And so lots of emphasis on heat pumps. A number of our listeners are primarily installing kind of the latest, technology that's out there, inverter-based modulating heat pumps. Are there particular areas within Manual S that you could touch on a bit more that address, those kind of heat pumps versus maybe a more traditional single stage or, 2-stage unit?
You get to do some different things when you start getting into more of the details. Unfortunately, I don't use it enough every day to quote all the details in there. But the coolest thing about this one to me was that the normative section, which is the actual requirements, that's the required parts of it that go into the codes, is all now free to view. You can get that on ACCA's website. So what they did is they used to have a normative section and an informative section, and that was all rolled into one book. You had to buy that book. So now what they do is you can buy a printed copy of it, but if you want to view it, you can view it for free online on ACCA's website. It's version 3 of Manual S, and they're going to come out with a guide, a companion guide. I think that's getting announced later this year or this winter. I think I've seen some stuff that Wes Davis over there at ACCA and Russ King are talking about that.
The main piece is that there's explicitly a section now that addresses inverter modulating heat pumps, whereas before it was a lot lighter on that. So now there's like a carve out, sort of what I think of in my mind for that kind of equipment, which is great because it wasn't as carefully addressed from what I remember in the previous version, and it empowers people to make better decisions and end up with better outcomes for that style of equipment.
Yeah, and really what happens with that is things like these standards are written for, they're written as a general, with general language for the whole industry. And they have to be updated periodically to keep up with the equipment that's in the industry. And the equipment has changed a lot over the years. And that's why these manuals get updated periodically. They're an ANSI manual, and part of being an ANSI approved manual is having regular updates done to it. There's periodic reviews, there's certain requirements for all this, and it has to go through certain steps in a certain time frame to get updated and get that approval. So that's all part of it. And if anybody ever wants to get involved with that, I highly recommend any of the ANSI approved manuals. Find the organization that kind of owns that manual and make comments. Get involved if you think you've got good information to improve it. Go out there and see if you can get involved, because a lot of them really want that input from the field, because if they don't have good input from field users, that's what makes the manuals usable to me.
That's great. ACCA is very good at convening from a whole bunch of different segments of the industry to make sure what they put out there is representing as much as they possibly can to have the best impact on homeowners. Great overview of Manual S. I'm itchy to get into the good stuff, which you had a bunch on heat pump performance, and you've hinted at some of it here with this new Manual S, thinking really about dehumidification and how you need to think about a heat pump performance if you want to cover 100% of the year. So let's get into heat pump performance. What do we need to know about what they can do, what they can't do, and what to watch out for if you're looking for a heat pump to do 4 seasons worth of work for a home?
Well, I mean, you really have to understand your loads on the house. That's where, your product like Amply comes in. It's making it easier for people to understand the loads on a house, which is great. But then you have to bring in the right equipment to match those loads, and you have to distribute the air, as we've talked about, in the house. I can't say it enough. Don't blow air on people. It's just not good practice, and you're going to have somebody uncomfortable at some point in time. You have to balance things in your setup, because as I said, comfort costs money. It's that we want to be able to deliver that comfort for the least amount of money possible. And that generally goes back to using the least amount of energy possible. I love what Robert Bean says about comfort and energy. If you've never heard that, he says, we design for comfort, energy is the scorecard.
That's
and
awesome.
That, to me, that's just like a huge reversal of what we end up with thinking about a lot of times. Because a lot of times we are asking people to design for quote unquote energy savings. I've asked this in a few of my presentations where I say, I'll ask the whole room. I said, how many of you have designed and conditioned a building and saved energy? You're not really saving energy. You're using energy to condition that building. We have to do that. If you don't want to use energy, turn it off and open the window. And that sounds a little harsh. And when you say that, it sounds harsh because it kind of is, but it's the truth. We want to be comfortable in our houses. That's why we build houses. That's why we, don't live in tents anymore. And we're going to use energy to do that. And we can reduce that energy usage as much as possible. But if we look at the energy, the cost of energy and the energy we save, a lot of times we're not going to pay for that work that we do to save, and I'm using air quotes here, save the energy or reduce our energy usage. It's very rare that we can reduce energy usage, especially with things just like equipment, just by changing equipment out. If we don't look at something else, it's very rare that we're going to reduce our energy usage enough to pay for that change out. But if we take in comfort considerations, now we're not putting a financial number on it so much. We're thinking about it from a human aspect. Maybe whether it's thermal comfort, maybe it's noise, maybe it's reduced pollutants or reduced dust in the air. There's multiple things here. And it's really hard to put a dollar figure to those. It takes a lot of work. Depends on what we're willing to pay for. But there's no free thermodynamic lunch. And I forget who said that or who I'm quoting on saying that, but I love that saying also.
Yeah, it's another good one.
So we really have to understand, like we said earlier, what the customer wants and then how we can deliver that. So when we're talking about designing heat pumps, we got to know things. How's that heat pump going to operate? One of the things I like to talk about is defrost. Most manufacturers have gone to what we call a demand defrost, where they just use temperatures to initiate our defrost. But there are still some manufacturers out there that use what's called time and temperature. And that means that there's generally timing pins or switches on there in every either 30, 60, or 90 minutes, depending on how it's set up. Whether it needs to or not, it's going to initiate a defrost. And those are still sold out there today in certain, and especially in lower end units. If you get into the lowest efficiency rating, what we can often refer to as builder grade units, because they're put into a lot of tract homes and things like that today, because they're the least expensive option out there. And when builders are building houses, they're looking to cut their expenses so that they can provide the lowest cost to the buyer as possible. And what happens is that cuts corners. That's the bare minimum. And a lot of those have that. And that ends up using more energy than you really need to. And it also can decrease comfort, because a lot of times there's a couple different ways we can do that. If you look at like a lot of the inverter, the mini splits or the ductless split units we use, they don't have any resistance heat in them. So they will really slow the blower down, because when a heat pump goes into defrost, it reverses its cycle. It goes into cooling mode. It draws a little bit of heat out of that house, puts it into the outdoor coil to melt frost off the coil. And normally when we have a unitary system that does that, we're going to turn on a little bit of electric heat, or we're going to kick into the gas heat if we're in a dual fuel to temper that air indoors. But that uses electricity. And the more often we do that, the more electricity we're going to use. And this was something I discovered on my house. I was playing around with this because I was like, okay, I want to try it without any electric heat during my defrost. I just wanted to defrost it. We're going to throw it into cooling. I'm going to see what happens. What I discovered was on the Bosch unit, it's what I call an airflow controlled inverter. So it modulates the outdoor unit based on the airflow indoors, or the amount of heat that's delivered to that indoor coil or removed from the indoor coil. So on low airflow or lower speed of the compressor, I can get away with that. I don't have to kick on any electric heat, because it's not putting out enough air right now that it feels cold to the occupants. They don't really notice it, not unless you're standing like right on top of a register, and that's not where you should be standing in a lot of the house. I don't have it set up that way. So in low speed, I can get away with that. But in high stage, I can't get away with that. It's noticeable cooling down. I sat there and I thought about it. I said, okay, well, I can turn the heat on. What I did was there's a wire that comes back from the outdoor heat pump that activates that heat. In common parlance, it's known as the W wire. So I had that disconnected, and I thought, well, if I connect that back up, there's a lot of the year that I run in low stage. And then I'm going to be paying for the heat strip in low stage as well as high stage. So I did something really simple with a relay. And when I'm in low stage, the relay's not powered. I don't power my auxiliary heat or that extra heat during defrost. I only power it when the blower's on high. And that's just, it's a pretty simple relay circuit to wire in. So that was, something I learned. And that's something it's unique to my house, but I think it probably might play across multiple things. So it's something for people to think about that's really pretty easy to wire up if you understand controls wiring a little bit. And if not, get with somebody that understands control wiring, and all you got to do is power a relay in that heat strip circuit that's powered by your W, and the relay's powered by the W wire coming back, or it's powered by the second stage. The relay coil's powered by the second stage fan call to activate, and then that passes your W signal back into the electric heat.
Elk, I just wanted to jump in. This is fantastic because it's such an important thing to emphasize. You got to know your equipment, know your controls, know what you're selling, and there's these small things you can do, like what it's putting this little relay in that dramatically improves comfort, and it minimizes that utility bill. So you're having a great outcome with just a tiny bit of extra work, and you figured this out because you could see, for your equipment, this is how the setup works, and I need to make this little tweak. So power, our knowledge is power, and small things can have big impacts.
And I know, some of this you can see, I think, and you prepared some slides on it about the performance curve for a particular unit, right? You can see what it's going to do in various stages.
Yeah, so let's take a look at that.
Yeah, I think it would be great.
We're going to start out with a single stage unit. And in this slide, what I've got is it's a plotted graph. We've got two lines on here, right? And the bottom line, when we talk about heat pumps, let's back up a little bit. When we talk about heat pumps, we talk about COP, or coefficient of performance. And we're comparing the amount of heat we get out of that heat pump to what heat we would get if we were using just straight up resistance heat and heating that house with a toaster. All right. So what we see here in this graph, the bottom blue line, is going to be the amount of heat I would get with a resistance heat. And I looked at the wattage that outdoor unit is using from the performance data charts. And I said, okay, how much wattage am I using at what temperature? And this is assuming it's perfectly charged with refrigerant, the airflow is set up properly, all that stuff. And how many BTUs would I get out of that if I'm just using it for electric heat? And then the top line, that green line up there, that line is the BTUs that I get out of the heat pump, right? When the heat pump is actually running. So that's what we call our coefficient of performance. And you can see even down there, this is a single stage, bare bones heat pump. Even down there at 5 degrees, I am getting almost twice the number of BTUs out of that heat pump that I would be if I was just using straight electric heat. So I'm taking that energy and I'm getting more heat out of it than if I'm just running straight electric heat. So even at 5 degrees, it's still cheaper, and you can interpolate these. This heat pump stopped at 5 degrees. It's going to make that graph is going to kind of probably tail off. It's not really ever going to meet until you get really, really cold outside. So let your heat pump run is what I'm saying here. And you're still going to get more value for your money out of that heat pump, even at extremely low temperatures, even if it can't totally heat the house, right? So we'll talk about that in a little bit. What that does, this next slide is with, this is an inverter-based, airflow-controlled heat pump, kind of like that Bosch that I have in my house, where the inverter. But that inverter allows us to get a little bit better performance here, right? And you can see the bottom blue line, we're actually kind of stepping up our wattage, and we're getting better performance out of it. And down there at 5 degrees, I'm getting more than double, right? So I have a COP of over 2 on that at 5 degrees. I'm getting way more of my money's worth out of that unit. So that is a little bit of the difference between just a single stage compressor and a simple airflow controlled inverter that I can still run off of a standard thermostat. I don't have to have a really expensive communicating thermostat to do that. So that's kind of nice to see that we're getting some more benefit out of those inverters. Now let's talk about taking that, and this is still a single stage right here. Okay, so we went back to the single stage here. We're looking at that house, or the performance line on the green line, and the blue line is now the house. This is what I need line. So if we plot those two against each other, if we know where our 0 point is, and I figured 0 is at about 70 degrees, you could actually probably back that off to maybe 65 degree outdoor temperature is, maybe where we would need some heating in the house. And then I took that down to 5 degrees outdoor temperature over here on the left. And where those two lines cross, that's where the heat pump, approximately where the heat pump is going to run out of capacity to keep that house warm. Now, this is fixed on a graph. In the real world, that point changes with outdoor conditions, because when we're doing our manual J load calculation, it is based on the dead of night with a certain amount of wind on all of the faces of the house. What's that wind speed, Eric? You can probably tell me that, right?
15 miles per hour. Yeah.
15 miles per hour on how many surfaces of the house?
That's the standard. Yeah. For a single family detached, it's all 4 surfaces. So yeah.
All 4 sides. Do they count that on the roof as well?
What I recall, it's just the vertical surfaces that we're really focused on.
Just the vertical surfaces.
For infiltration, it's 3 or 4 sides. Then if you get to like a condo or, some kind of different housing configuration, you're thinking about 1 or 2 sides.
Yeah. So that really depends on that. But yeah, so if we don't have any wind, or we have, say this right now on this graph, this one crosses at about 28 degrees Fahrenheit. So if we have a 28 degree day where it's sunny outside and there's no wind, right, that cross is going to move to the left a bunch, chances are. So I'm actually going to be able to run that down low. This is where, to me, I like to control my auxiliary heat and my staging based on an indoor temperature rather than a strict outdoor temperature, because I can maximize my value and my comfort with that. It's a balancing act there.
And for folks who are listening, we've got a chart that looks like an X that is the graphical representation of why many folks are scared to install heat pumps. Like, we're seeing the point at which you're worried the heat pump isn't keeping up. And Elka's doing an awesome job explaining why there's like a whole bunch of nuance there. It's not just at 28 degrees or whatever that point might be for your location. This is great, Elk. Keep going.
Well, and some of the other things too are, as accurate as we try to make our load calculations, our load calculations are never going to be 100% perfect, because we can't always get every single nuance of a house into that mathematical calculation. So there's a little bit of squish in there. And I've seen that a lot of manual J calculations tend to overstate heating a little bit. So a lot of times what we hear is, oh, well, the heat pump won't heat the house anymore, so now I have to shut that off, go into emergency heat, and now I just want to run straight electric heat. Well, why? I'm still getting way more value for my money down here with that heat pump, and I can maybe add on a little bit of electric heat. Like this first gray line here is 5 kW of electric heat. So I can just run that 5 kW. Otherwise, I would need that full 7.5 kW more than likely to control that house. But I can cycle 5 kW off and on while I'm running that heat pump continuously to control the temperature in the house now. So that maximizes my comfort and maximizes my energy usage, because I'm running that heat pump continuously. So I'm constantly adding heat to that house to help control those surfaces. But I'm cycling that 7.5 kW off and on to go ahead and just keep that temperature bumped up occasionally. So I'm stacking right there. I'm stacking heat sources. And then when it gets really cold, maybe I might need to add in another 2.5 kW for this particular application here. to be able to control that house and keep that house at temperature. Right? So if we go on to our next slide, you're going to see a similar x-axis, but I'm not going to need electric heat until I hit about 15 degrees is my calculation. Now, this one actually happens to be my own house. This is a graph I did for my own house when I did early on. And what I found is that when I watch the heat strip application, I'm actually running my heat pump down closer to 5 degrees, down in the high single digits before I need to kick on any auxiliary heat. So I'm carrying that. My design conditions here are 5 degrees. So I'm carrying that darn near to 5 degrees before I'm going into auxiliary heat.
It's not like you're turning off the heat pump then. The heat pump keeps going. You use it to augment, purely.
Correct. Just augment that heat pump. Just because the heat pump can't get quite enough to keep that house at set point. So I'm going to augment it. But I'm still getting way better value for my money. As we saw, I'm probably getting a COP of 2, high single digits, 1.9 or maybe 2.1, something like that at 5 degrees. So way better value for my money to get that heat out of it. But sometimes I'm going to have to supplement that for comfort reasons because I don't want the house to fall down because I like to be pretty comfortable in the house.
And Alec, I think it's such a great moment here just to reiterate one point you touched on with the control setup. Whether you've got a communicating thermostat or a non-communicating thermostat, you typically, again, if as long as it's a modern type of controls, you have an option to specify, hey, heat pump, you must cross over and start using auxiliary heat at X temperature. Or you typically have an option to say, let's do it based on, how long it's taking to achieve, to satisfy the thermostat. So if it's taking more than half an hour, 90 minutes, whatever you set it to, then I will switch over and, add in some auxiliary heat strips. That latter option allows the system to truly find the optimal place to do that changeover, as opposed to just kind of guessing at it. So as those wind speeds change outside in the wintertime, or whatever dynamics are happening in your house, the system will find that optimal place to operate.
Yeah, and something else that happens on houses a lot in the wintertime in certain parts of the country is snow load. Well, snow is a fantastic insulator. I mean, people build huts out of it in the far north, all the time. They're called igloos. They used to live in them year-round. Well, not year-round, but they used to live in them a significant part of the year because it's a fantastic insulator. So if we add a bunch of snow to that roof, is that built into our load calculation?
Sure isn't.
You guys can't build that in, can you? Because you can't predict it.
That's right.
It's not a predictable value. So if we get a bunch of snow on the roof and it helps to insulate that roof, it reduces my heat loss. Well, now I can make that point, that slide down lower because my heat loss has been reduced. But it's not a predictable item. It's not something we can control. It's kind of like shading from a tree. It's not something we can really control all the time. That's where I love to let that thermostat do it. Like the thermostat that I use has what they call a comfort algorithm in it. And I set my staging a lot of times on that comfort algorithm until it gets really deep down into the staging. Because on my particular one, I have 4 stages of electric heat. I go ahead and let that comfort algorithm go. And what it does is it looks at a combination of runtime, and it's also looking at the temperature in that house. So it's saying, okay, is my temperature holding steady, or is it ticking down? Because it can look at it in tenths or hundredths of a degree that we don't see on the display, and we don't want to be able to see on the display, because then we're just going to sit there and watch the display and obsess over that display constantly, because that's human nature. But it can look at that internally and make that decision about, hey, my temperature is just slowly ticking down, ticking down, ticking down, ticking down. I'm going to go ahead and bring on the next stage, because even though I'm running this one, it's not going to satisfy, and it's going to go ahead and bring that other one automatically. So there's a lot of different options out there for controls, and some of them are communicating, some of them are not. There's different features to each one. Kind of have to decide in it, and it's really challenging because they a lot of the manufacturers don't really tell us how some of these things work, especially when they call it their proprietary comfort algorithm or something like that. They're going to hold that pretty close to their vest. They're not going to tell you exactly how it works other than it just does it and it maximizes comfort. Or you can set offsets in there. Some of them will say, okay, if it drops a degree below set point, then we're going to go ahead and bring on the electric heat. We're going to bring on the next stage. Or you can do it like you mentioned with a time thing. If this thing's been running for 45 minutes, some of them do a time. If it's been running for 45 minutes and it's still falling, then we're going to bring on the next stage. There's all kinds of different ways to do that and to program that logic in there. So let's hit on this one. This is cold climate heat pump. And you can see if you're looking at that bottom graph, those temperatures go a lot farther to the left. I've taken that one out to -10 Fahrenheit. So we can see there that particular one, this shows the blue line is the heat loss on the house, or my minimum running, my minimum BTUs on that heat pump, and the green is the maximum. So where the yellow line crosses the blue line, to the right of that, we're going to be doing an on-off cycle. To the left of where the yellow and blue meet, all the way over to where the green and the blue meet, we're going to modulate that heat pump somehow. So this is an inverter heat pump. It's got a communicating thermostat on it. And then at that point, that -3 or whatever that is, where the blue and the green cross, that's about where we need to start bringing in our auxiliary heat if it's necessary. But again, if it's the middle of the day and it's that temperature, we might not need to bring that auxiliary heat in at all. It all depends on what that house really needs. So allowing that control to kind of watch the house and figure out what it needs. And control placement is a big one on that too. Okay, so this is a graph and we're looking at the cooling side, the heating side. We're looking at the green lines are the load of the house. And the red and blue lines up there are the heating and cooling performance of the equipment. Okay, so this is maximum heating and cooling performance of the equipment. And this is going to be the minimum heating and cooling performance of that equipment. And this is where we get in, this kind of leads to where we can get into trouble with our equipment, because a lot of times we think about modulating equipment. Hey, it's going to modulate and match the load. And this really shows the segments where we have to look at. So our gray segments down here is where we're going to have on-off cycles. So this particular one is pretty well suited for heating. If this house, if that design temperature was 10 or 15 degrees, because that's where our load and our equipment capacity meet. Below that, in this orange segment, we're going to have to use the equipment plus a little bit of supplemental heat to meet the demand if we're at 100% design conditions, which is admittedly hard to arrive at sometimes. But down here in this yellow area, we're going to be able to modulate, right? That's going to be a real nice area. We're going to be able to modulate, run that heat pump at 100% of the time to offset the constant losses that the house has and deliver that premium comfort. And then down here in this gray, right, this is where we can get into trouble, not so much in the wintertime by turning the equipment off and on, but where we get into trouble is in what we talked about, and this is what Manual S helped to address. We've got to cycle that equipment off and on. And what happens is, especially with inverter equipment, it's not like single stage where we just flip a switch, turn the compressor on, it runs. It takes some time to get ramped up. I think you said you've seen as little as 5 or 6 minutes on this now, Eric, and I've seen as long as like 13 to 15 minutes to get ramped up from 0 all the way to that compressor running at its desired speed. And if that's cycling off and on, it's a very real possibility when the load is low in there that it could satisfy that thermostat before it gets up to full speed, which means no dehumidification. So in this gray area down here on the cooling side, that's where we really need to, with this particular combination, and this happens a lot in heating dominant areas, this is where we may need some supplemental dehumidification, things like that. And that's where the Manual J info feeding into Manual S can really help us with that guidance of saying, hey, I might need some supplemental dehumidification, something like that, and to get things sized well and sized properly.
Totally. And this is looking at the chart where this is the time of year, at least on this chart, where it's 70 to 80 degrees. It's not blistering hot out, but it's these shoulder seasons. You got these very low cooling loads that you're getting at, where you might need that supplemental dehumidification. And because you've got that low sensible load, you're satisfying really quickly. That's where you got to watch out. So it's a surprising little nuance that a lot of folks are not thinking about.
And it's a nuance that can get us into a lot of trouble because humid environments aren't good for the occupants from a thermal comfort standpoint. They're not good for the occupants a lot of times from a health standpoint. There's a lot of factors that go into that. So, it's something that we definitely have to consider as practitioners. And I ran the no load on cooling down there at 70 degrees because a lot of times on these days, yeah, the air temperature is not bad, but we're going to get can get a lot of load from direct sunlight. And we get a lot of cooling load from direct sunlight to control those mean radiant temperatures. We want to control those surfaces in there. And that's where even doing a circulating fan on something like that, if the circulating fan is blowing on those surfaces well, that circulating fan can help control that.
I love this chart because you can, again, folks who are listening, really encourage you to check this out on YouTube or in our show notes. There's just I'll call them the two happy triangles for an inverter heat pump where you're just fully modulating both in the heating season and the cooling season. And then there's sort of these danger zone triangles where maybe you need some supplemental or auxiliary heat way out in the extreme ends of the heating season. But then you need to watch out on that kind of the early part of the cooling season where you have these zones where you're going to be doing a lot of cycling, and depending on how many hours you're spending at that point in your location, you may need that extra dehumidification.
Yeah, and it's definitely a concern that we have to watch out for because it's, as we said, comfort, health, all kinds of stuff.
This is so helpful, Elk. I really appreciate you going through these slides. It was when we saw them the first time at the Heat Pump Summit last summer. It was illuminating and informing, and it was actually super fun for me to go through them again. I picked up a few more details myself. Yeah, just before we wrap up, I'd love to hear if there's anything else that you could recommend to our listeners. Any key resource that's really helped you in your career. It could be a podcast, it could be a book, it could be a person. What else would you recommend folks check out?
Oh my goodness. There are so many great resources out there that have helped me along. Some of them aren't even in existence anymore, but finding a good source and a good, I'm going to say a tribe of people to hang around with. There's a lot of resources out there on the internet today. I tend to gravitate towards Facebook and LinkedIn because they're a little bit more conversational, whereas some of the other stuff is it's a little harder, I find, to converse and have a back and forth dialogue, ask questions, get answers, share information like PDFs and links and other outside data. Those are kind of the two platforms that I gravitate towards and in discussion groups there. And I've found so many great people across this industry and many other industries that have helped me, and I try to help them whenever possible. And just, we all kind of work together and grow together. Find your tribe, find some great people that are willing to help you.
Love that. So that's great advice. Eric, thank you again for joining us on the Heat Pump Podcast. It's been so much fun.
Thank you for having me. This has been a great time.
Thanks for listening to the Heat Pump Podcast. It is a production of Amply Energy. And just a reminder that the opinions voiced were those of our guests or us, depending on who was talking. If you like what you've heard and haven't subscribed, please subscribe in your favorite podcast platform. We'd love to hear from you, so feel free to reach out. You can reach us once again at hello@amply.energy, no.com, just .energy. Thanks a lot.